Okay, this video is going to discuss some details of generalization in operant conditioning. Remember how back in respondent conditioning, that Pavlovian stuff, we saw generalizations such as this graph on the right. Like if Pavlov had played a 500 hertz tone prior to giving his dogs the meat, and he did that over and over and over again, 500 hertz tone as the conditioned stimulus and meat as the unconditioned stimulus, we would soon find that the dogs start salivating to the 500 hertz tone by itself. That's plain old acquisition of respondent conditioning, right? They're salivating and responding to the conditioned stimulus alone. That's respondent conditioning, but we also saw the dog might start salivating to other tones like 400 or 500 hertz, 400 or 450 hertz or 550 hertz, things like that, even though those were never played prior to getting meat. That was generalization, when things similar to the CS manage to also elicit the behavior sometimes, as long as they're similar enough to the CS. Well, that was for respondent conditioning, but a similar idea of generalization applies to operant conditioning, where we're dealing with behaviors that are a little more under the organism's control, behaviors that we emit, rather than ones that are elicited reflexively by a stimulus. So, specifically, let's just start with the simplest operant conditioning situation. So in a particular context, there's some discriminative stimulus, an SD, that signals to me a behavior will be reinforced. If I do the behavior, I get reinforcement. Like when I say sit, that's a discriminative stimulus that tells my dog, right now the sitting behavior will be reinforced. Or in this case, I might turn on a blue light, and that tells a rat that pressing the lever right now will be reinforced. Assuming the rat has been in this circumstance for a while, that we've done this training for a while, like 100 sessions or something like that, he's going to do a certain rate of the behavior when the blue light comes on. That makes sense. The rate of how much he does the behavior, it's going to be a function of what schedule of reinforcement we chose, but eventually he's going to settle into some consistent and steady state of performance, right? So the question is, what happens if then I don't turn on that blue light, but instead turn on some other lights that were not involved in any of his past training? I might turn on a red light and maybe he doesn't do much of the behavior at all, but what if I just do some different shades of blue or some things that are kind of like blue but a little different like green? So what we might find is something like this graph here, where on the left, on the y-axis, we've got the number of responses, or maybe this could be the rate of responding when we turn on any of these stimuli, right? So if I try colors that are similar to the SD, the one that was used during training, I might see a rate of behavior that's not quite as high, but somewhat similar. Whereas if I turn on a light that's pretty different, a little further away, I'll get much less behavior. We actually call this graph here a generalization gradient. Basically, after reinforcing a behavior to a particular SD, you test some other stimuli and see how much the R shows up to those other things you never trained. So to construct this graph, to map out the generalization gradient, you just have to test all those stimuli without reinforcing them directly. Maybe you do this as a probe trial. So during all that training, after you've done hundreds of trials, occasionally you just throw in a different color light and see how much they respond when that one's on, right? But in those probe trials, you might just test those stimuli without reinforcing them directly. So you know they've never been reinforced for that color. Just see how much the stimulus itself produces the behavior based on all that experience they had with the discriminative stimulus, right? So for example, imagine I do this procedure for a couple groups of rats. Like for one group of rats, I turn on a 530 nanometers light and I reward them for lever pressing during that time. And imagine I do the same procedure for a second group of rats, but for them, I'm turning on a 580 nanometers light and I reward them for lever pressing during that time. So I got two groups of rats just being trained to slightly different lights, okay? Note that there's no S delta here. There's no extinction condition for either of these groups of rats. There's no extinction condition. Just a plain old kind of simplest possible situation of a particular light comes on that signals now is the time when lever pressing is rewarded. But for each of these groups, the light they've trained on is a different color. Now, once the training is complete and they've got that down pat, we might test their generalization, right? We might want to construct a generalization gradient for each of these groups. So we just test them out on some different lights, some ones that they never learned, right? And see what they do for various lights. So this graph here on the left, that's the actual result when we try it. Group 1, the solid line here, group 2 is the dashed line here further to the right. Notice a couple things about this. Group 1 never presses the lever at all to a 600 nanometer light. Whereas group 2, right, they never respond to a 500 nanometer light. There's some differences there. Notice the stimulus that each group responds the most to, though, where the peak of this graph is for each of these groups, is right where we've been doing the training, the one they were directly reinforced for, and they're getting less responding for stimuli that are more and more distinct from the SD. So the SD is where we find the peak of responding, right? The one that they've been trained for. This is what we'd expect, a generalization gradient centered right around the SD that was present during all of their learning. Now, just remember that the generalization, it's the opposite of discrimination. So the graph could have looked a little bit different here, right? We can look at how peaked the graph is. The generalization gradient could be kind of more spread out or more of a really kind of tall, sharp peak. So if we saw a really sharp, tall peak right at the SD that we had trained them on, like the dashed line in this example, we would say there's a lot of discrimination going on, not as much generalization, right? They don't do as much. If they were trained on the 1000 hertz tone, that's our SD, the discriminative stimulus that we turned on when they were rewarded, we see that for this group with the dotted line, there was not as much not as much generalization, so they don't respond much at 450 or 300 hertz, at 2250 or 3500 hertz. But the solid line here that's more flat doesn't have as much of a peak at the SD. That would mean their responding is less specific to that 1000 hertz tone that we had trained them on and more generalized to other tones that are similar. So the solid line shows higher generalization and lower discrimination compared to the other line. Now in a bit, we'll come back and explain why the dashed line here might also just go so much higher overall, have a peak that goes so much higher, get so much overall behavior more, but we'll come back to that. First, let's just keep going with this generalization gradient stuff. Here we've described what happens in the most simple training where you were using an SD, like a 1000 hertz tone, and just testing. You haven't trained anything else, but you're just kind of going to test what other things set off that response. But there was no S delta responded in this training. There was no specific light that you were turning on to tell them, oh, you won't be reinforced, right? But what happens during something like discrimination training that we've talked about when we use both an SD and an S delta for a while? Like a green light means the behavior will be reinforced, and a red light means the behavior will not be reinforced. That would be a discrimination training. What does the generalization gradient look like when we then test out a bunch of random ass lights just beyond like the ones that they had trained with, the green and the red ones they'd learned in training? So imagine during discrimination training, our SD, the one we're rewarding, is we're turning on a light that's 550 nanometers. But we're also spending a while on an S delta, which is a light of 570, like you see labeled on the x-axis here. In other words, when we flick the SD on, they've learned that doing the behavior leads to reinforcement, but when we flick on the 570 S delta, it doesn't work anymore. We give them lots of experience with these two stimuli during that discrimination training, but then we want to test their generalization, right? We want to test out a bunch of other lights, a bunch of wavelengths they've never experienced before. So that 550, that's kind of a greenish yellow, and 570, that's kind of an orangish yellow. What happens when we try a pure yellow that's halfway between those at 560? Or a more green color like at 520, or a more orange color like at 580 or 600. Let's see what happens. Here's the data. When we do the training, right? We did the training. They were rewarded at 550. They were not rewarded when the 570 light was on. Here's what we see when we test out a bunch of lights and draw the discrimination gradient. So I want you to ignore the solid line here. I want you to look just at the dotted line because that's our discrimination training condition. That's the one that we actually just talked about. Ignore the control condition with the solid line. The dotted line is what our data actually looks like for this procedure. We train them to discriminate 550 from 570, but then when we test a bunch of other colors of light, we get this kind of weird pattern. The peak where they respond the most, right, the high point here in the graph, is not at the SD. It's not at 550. The thing that we were directly rewarding all along, that's not where they're responding the most. Rather, the peak is shifted over to the side. We're getting the most responding in a color of light we never directly reinforced at all. That wasn't there at training at all. This effect is called peak shift. So the peak, the center of the generalization gradient, is shifted kind of extra far away from the S delta. So they respond the most to something that's even past the SD, despite the SD being what was reinforced the whole freaking time. It's a bit counterintuitive, since you would think they would respond the most to the thing you've been rewarding them for directly all along. Now, the control condition here, the solid line, by the way, that's for our simpler form of training where we just reinforced the SD at 550 nanometers, but didn't have an S delta condition at all. So there we do get a pretty symmetrical gradient, which has its peak right where we might expect, at the SD that we trained, right at 550. But when we use an SD and an S delta, we get that peak shift off to the side. Here's another example. The S plus, by the way, here, they just mean that's our SD. That's the discriminative stimulus. That's the one during training that means the behavior was reinforced. So when a 550 nanometers light was turned on, the behavior is getting reinforced. Now let's consider the three different lines here. These are three different conditions that we can test out. So first, the black line, that's our control condition. There's no S delta there. We just did simple training with the 550 nanometers SD, and sure enough, we get a nice symmetrical gradient centered with a peak right where we trained it, right at 550. That makes sense. Now let's consider the red line. In that one, we used an S delta of 590 nanometers. So the S delta was way out here. So a light that was like out here, we turned that one on, telling them it won't be rewarded. And then we spend a while with this light on, telling them they will be rewarded. Then a 590 where they're not rewarded. And then a 550 where they are rewarded. And then a 590 where they're not. That's what the red condition is, okay? So the 590 signal, it's a signal that the behavior won't be reinforced. Notice though, the peak of our red line, the peak of behaving for the rats or the pigeons in our red condition, it's shifted to the left of 550. Specifically, it's shifted kind of to the opposite of where 550 is, to the opposite side away from the S delta that we were using. So the peak of the graph goes further away from the S delta. Now in the blue line condition, we used an S delta of 555, right up here, really similar actually to the SD, right? So we use an S delta of 555 nanometers. Once again, we see a peak shift for the blue line. The peak of the blue line is to the left. It shifted away in the opposite direction from the S delta. In this case, even further away. So like notice in the blue line condition, the S delta is really similar to the SD. 555 nanometers means no reward, but a very similar light, 550, means you do get reward. They really have to attend to that subtle difference in order to succeed here. And that seems to shift the gradient even further to the left. They did not respond at all in this blue condition to 560 or 570 or 580. Whereas in the red line condition, the SD was rewarded at 550. That's the same, right? But the S delta is pretty different all the way out there at 590, the place where they're not getting rewarded. So there the peak shift happens in the red condition, but not as intense. Notice in that case, for the red condition, you'll see some responding at 560 and 570, even a little bit at 580, but still the whole graph is shifted to the left so that the center of the gradient isn't above 550, where we might have expected it, because that's what we were rewarding the whole time. It's shifted further to the side, away from the S delta. Now the real question is, why does this peak shift happen? So here's one way to think about it. Imagine I train some organism, right? A child, a pigeon, a rat, whatever. I train this organism to discriminate this SD, right? This kind of gray color from this S delta here. These two shades of gray. One pays off, the other doesn't. When one light is on, the behavior works. When the other light is on, the behavior doesn't work. Now during that training, I wouldn't always put the dark one on the left, just to be clear, because I don't want them to simply learn the rule that the left button is correct. So on each trial, it'll be random which of these two stimuli I put on the left or the right, right? They have to respond based on the actual color in order to get the response, in order to get the reinforcer when this color is present, okay? So I train them on this for a while until they've really got it down. They can tell the difference between these two colors. Discrimination training is done. The discrimination index is high. They can tell these two stimuli apart and they behave very different to them, okay? Then I do a test. I give them these two stimuli on the right, and I see which they pick. Again, I could put either of these colors on either side. I do it just randomly. I just want to know what they'll pick when presented with one of the old stimuli that they had some experience with, and a brand new stimulus. So pause the video for a second and just take a guess at what they'll pick. Well, it turns out they actually choose the one on the right here, which is kind of weird because that's the freaking S delta. That's the color they were literally trained to avoid for a very long time. They were really good at avoiding it. And now in this new situation, they choose it over the thing they don't know. So what's going on here? We think that peak shift might actually be due to what's called the relative nature of stimulus control. Basically, the probability of response is controlled not just by your direct experience with the stimulus itself, but by the difference or the comparison between different stimuli. So in discrimination training, we learn about the comparison, not the specific absolute value of each stimulus. This is actually referred to as relative stimulus control. Organisms, they often respond to differences in stimuli. In discrimination training, then, we might be learning that the SD is something like larger or greener, not that this exact shade of light, this exact shade of light green or this exact shade of dark green, something like that. We might be learning more relational comparisons between the two stimuli. So basically, in that example a minute ago, maybe they weren't learning that the SD is this shade of gray, right? The absolute color here. That might not be what sets the occasion for the behavior to lead to a reinforcer. They might be learning to choose the darker shade. That's the rule they're learning, and that's why when presented with these two options, they choose the darker shade expecting a reinforcer. That would be relative stimulus control. So if we spend a bunch of time training them to respond to like this lighter color here on the left and not to respond to this darker color, that's our S delta, then we test them by offering, these two options here, like that kind of darker, what was the S delta versus some brand new stimulus that's even darker than that. They choose what used to be the S delta, even though it wasn't rewarded before, because it's the lighter of the two options. So the whole time, we thought we were training them to understand two different stimuli independently, but they were actually learning about them simultaneously in a relative or comparative manner. That's the idea of relative stimulus control, and it's one really good way to explain why we would see peak shift. That said, there is an alternative explanation which also would account for peak shift. So this guy, Charles Schimp, he actually came up with another kind of theoretical way of explaining peak shift. Basically, his idea was that all those times that we were rewarding the SD, it was basically creating a perfectly normal generalization gradient based right at the SD. Not shifting at all. There's no peak shift or anything at this point. You could think of it like just an excitatory effect. Things that are similar to the SD make me more likely to respond because they're similar to the SD. It's a nice simple generalization. So you can actually see that here in the dark black line here. This would be the generalization gradient right around the SD, the 550 that we were training them on. So that was our SD. That's the thing they're getting rewarded for. And we get excitation kind of equally on both sides of that. Nice symmetrical, just generalized excitation around the thing they were rewarded on. But we also have those trials with an S delta at 570 nanometers, right? For discrimination training, we've got an S delta. So if it's at 570, what's happening is responding is not reinforced there. In that case, we're learning not to respond to the S delta, not to respond to 570. And Schimp thought maybe that creates a sort of inhibitory gradient, a sort of upside down gradient. It makes us much less likely to respond at 570 where the S delta is, but also less likely to respond to things that are similar to the S delta. So we get some inhibition near 570, at 580, at 560, and maybe a little less inhibition at 600 or 560, and so on. It's a sort of upside down generalization gradient like the bottom graph here, since it's inhibitory, makes behavior less likely for that stimulus and for the stimuli that are kind of like the S delta. So his insight was that these two things might be happening simultaneously. They might kind of combine or cancel out. So what we're seeing in the actual behavior, in the peak shift graph showing their actual responses, what we're seeing is just the net response gradient, which sure enough, if you combine that solid black line in the top there with the light gray line at the bottom there, you actually get the medium gray line in this top graph here. Basically, if you go a little to the left of the 550 SD, like at 540, you've got a lot of generalization, a lot of excitatory generalization. But at 540, you're not getting very much inhibitory generalizing from that 570, right? Because it's pretty far away. So you're not getting much inhibition, but you're getting a lot of generalized excitation. So the net is quite a bit of behavior, right? Whereas at 550 itself, the thing we were training the whole damn time, yes, you have a little more excitatory effect, but you've also got a lot more inhibitory canceling it out, which is why the maximum responding isn't right there at 550 where we were directly rewarding them the whole time. It's shifted over to the left. So this is another way of explaining why peak shift occurs. We won't get into the kind of complicated ways to try and distinguish this explanation from the relative stimulus control explanation, but I'll just say there are plenty of data to support the idea of relative stimulus control for many behavioral situations, so it's kind of good to understand regardless. We often learn things in relation to other things. Finally, coming back to that, a side note here, I mentioned in passing when we first saw this peak shift graph before, notice we've got more overall responding, just literally a higher peak in the discrimination training group, the ones where there is an S delta, right, an SD and an S delta. That's our dotted line graph. We just get overall way more behavior compared to when there's only an SD during the training but no S delta, our control condition. So why might that be? There's actually something we learned in the last video which might explain why the graph gets so much higher when an SD and an S delta are involved. Pause the video, see if you can make that connection. So what's going on here is actually behavioral contrast. The S delta condition sucks, giving no reinforcement, which makes the SD condition relatively better, thus increasing its behavior, giving us a lot more responding than we would for that same schedule of reinforcement on its own. So we've got positive contrast here, more responding on the SD schedule than we would normally experience because there's an alternative to it, which is so crappy. All right, well, in this video here, in the next one, we're going to play a little learning game. And then the final video for this topic will cover concept learning and see some applications to things like memory.